I'm setting an extra additional question on pendula. A few people have said to me that they didn't see the derivation or the questions were quite confusing. So please find these questions attached, have a go at them, and I'll go through them. I suggest don't just watch the video and go, oh, I'll understand it, because it's never quite the same as actually trying it yourself. But if you have a go at them, and if you get stuck, maybe watch a little bit of the video, and then see if you can get going there. They are quite challenging questions, but they show lots of the key points, including some of the stuff on energy we're doing this week. So this is taken from Hutchins' book, and it's question 10.9. So the first bit is show the time period of t of a small amplitude oscillations. A simple pendulum are given by length L are given by t equals 2 pi root L over g, where g is acceleration due to free fall. So this is part A. So this is in essence a derivation of the time period. So we draw the pendulum at an angle theta, and we've got to label the forces on this. So the first force is mg, that is there. And there is the tension there. So you can see that these forces don't act in opposite directions, and they're not necessarily equal magnitude, and therefore there is a resultant force on this. The resultant force on this pendulum is acting towards the equilibrium point down this way, and that is what causes the pendulum to oscillate. So what we do, this arrow should be a little bit longer really, there. What we need to do is we need to resolve these. So what I'm going to do is I'm going to resolve the two components of mg. There is mg component in that direction, and there is a component in that direction. This acts tangentially to the arc of the circle in that direction there. Now the bulb is not moving up or down in this direction. Therefore these two components are equal to each other. This component acting in this direction has no force opposing it, and therefore this here, this arrow here, is the resultant force. On the pendulum bob. So we need to work out what this force is here, and this here is theta. Because this point here is vertical, the weight acts down vertically, and that is all in one line there. So if that's theta there, that is theta there. Just to make this a little bit clearer, what I think I'll do is I'll just redraw this force triangle here. So what we've got here is we've got mg, and then we've got two components, one component there, and that is theta. And this here is the resultant force, which I'll use sigma f. So that's the opposite, and that's the hypotenuse. So we're going to use sine. So sine theta equals, or the resultant force is equal to mg sine theta. Now this is a simple harmonic oscillator, and therefore the only force acting on it is that, and therefore we can apply Newton's second law. So I'm just going to move my camera a little bit because I'm a bit off screen. There you go. So applying Newton's second law, resultant force equals ma, which is equal to mg sine theta. So we have this equation here with the sine in it. The sine in that is really not very helpful because for simple harmonic motion, displacement must be directly proportional to acceleration. So we need to get rid of that sine there. What I'm going to look at is I'm going to look at the arc length produced here. So I'm just going to draw another copy of that diagram there. So I've got theta here. This length here is L, the length of our pendulum. That's important. That's the distance between the centre of mass of the pendulum and the pivot. And we've got our arc length here, which is our displacement. So in a pendulum, the arc length is how far it is displaced. So our displacement is the arc length from the equilibrium point here. So you're familiar, hopefully, with S equals r theta. So using our notation here, our arc length S is x, our radius is our length L, and our angle there is theta. You'll quite often see in a question, and it says small amplitudes. This bit here, small amplitudes, that tells us that we can use the small angle approximation. Okay, so we can say that theta is equal to x over L. I'm just rearranging that. I should have done that before I went through small angle approximation. And we can say that since theta is small, now it's normally taken as less than 10 degrees, sometimes 15 degrees there. Since theta is small, theta is roughly equal to sine theta. So I can take this equation from up here, and I can go MA equals mg theta. I can cancel the m's, and I can then substitute in for theta from here. Okay, so theta is equal to x over L. So we've got A equals g x over L, just fitting on the page there. I'm just going to write this in a slightly different way, hopefully to make it a little bit clearer, and I can go A equals GLX. Now we know that this is simple harmonic motion. We're told it's simple harmonic motion, so we can compare this to A equals minus omega squared x. I've done it again as one of my other videos. I've forgotten the minus sign. We should have a minus sign in here, because the acceleration is in the opposite direction. So if that's our displacement that way, then the acceleration is in that way there, and they're in opposite directions. So we have the minus there, so we have the minus there. And from this, therefore, we can show that omega squared equals g over L square root, both sides, g over L. We know that omega equals 2 pi over t. So 2 pi over t equals root g over L. Flip both sides. So t over 2 pi equals root L over g. And therefore t equals 2 pi root L over g, which is our equation for a pendulum. So just a reminder, that's how you derive the equation for a pendulum. There's a few important points that you will need. You don't need to be able to do the derivation in its entirety in the exam. You must be able to draw a force diagram and identify what the resultant force is there. You must be able to identify this equation and compare it to omega. A is minus omega squared x, and you must be aware that we use the small angle approximation, and that's why the equation for a pendulum is only true for small angles. So that is the end of part A.